rotating about the y-axis. Like the disk method, the washer method has an analog for regions revolved about the y-axis. If the region below is revolved about the y-axis, then the cross-sections are still in the shape of washers, circular disks with holes in the middle, but the cross-sections are now perpendicular to the y-axis. This means the inner radius, v of y, and the outer radius, u of y, are now functions of y. Thus, the volume formula is given by the antiderivative from c to d of pi times the quantity u of y squared, that is your outer radius squared, minus v of y squared, which is your inner radius squared, with respect to y. Generally, when you have a function of x that is being revolved about the y-axis, you have to solve it for x in terms of y. The integration is done with respect to y. Now we're going to look at an example of an application of the washer method. This time we will be revolving about the y-axis. The directions here are to find the volume of the solid that results when the region enclosed by the given curves is revolved about the y-axis. Here we have the curves y equals x squared minus 1, x equals 2, and y equals 0. So we will begin by labeling the curves. Here we have y equals x squared minus 1. Here we have the line x equals 2. And here we have y equals 0, which is just the equation of the x-axis. We are rotating about the y-axis. So before we can begin to calculate the volume, there are a few preliminary calculations that we have to make. First, since we're revolving about the y-axis, we need our functions to be functions of y. Okay, so here we have x as a function of y, just a constant function, but here we have y as a function of x. So we need to begin by solving this equation for x. To do that, we have y equals x squared minus 1. We begin by adding 1 to either side of the equation. This will give us y plus 1 equals x squared. Then we take the square root of both sides, so that x is equal to the square root of y plus 1. So we'll go back to the equation here of y equals x squared minus 1 and write the equivalent function of y. X equals the square root of y plus 1. So that's the first thing we needed to do. The second thing we need to do is to find our bounds of integration. We know the lower bound of integration, it's y equals 0. But now we have to find the upper bound. So we need to know where the line x equals 2 intersects the curve x equals the square root of y plus 1. To do that, we will set the curves equal to each other. 2 equals the square root of y plus 1, and then we will solve the equation for y. We begin by squaring both sides, so that 4 is equal to y plus 1, and lastly we will subtract 1 from both sides, so that y is equal to 3. So the lower bound of integration is 0, and the upper bound of integration is 3. Now we can begin to find the volume of the solid. The inner radius is x equals the square root of y plus 1, while the outer radius is the line x equals 2. So to find the volume, we will use the washer method. The volume will be given by the antiderivative from the lower bound, which is 0, to the upper bound, which is 3, of pi times the outer radius squared, the outer radius in this case being 2, we will square that, minus the inner radius squared. The inner radius is the square root of y plus 1. And we square it, and we will integrate with respect to y. To simplify, we will remove the pi and multiply it on the outside of the integral. When you square 2, you get 4. And when you square this radical, the radical is removed. And so you have y plus 1. And all of this will be integrated with respect to y. We can clean it up even further by distributing the minus sign here, which will give us pi times the antiderivative from 0 to 3 of 4 minus y minus 1. Again, with respect to y. At this point, you can go straight to the graphing utility to compute the volume of the solid. We will compute the antiderivative from 0 to 3 of 4 minus y minus 1. When we get the answer, we will multiply it by pi, and that will give us the final volume. To compute the antiderivative, we will select the Math menu, and under this menu, the ninth option, FNINT. Our function is a function of y, but for convenience, we're going to use the variable x. So instead of inputting 4 minus y minus 1, we will input 4 minus x minus 1. Follow that by a comma, and then x, which lets the calculator know that we are integrating with respect to x. We follow by another comma, and then input the bounds of integration. The lower bound is 0, and the upper bound is 3. We close the parentheses and hit enter. We get an answer of 4.5. To convert this to a fraction, we will select the Math menu again, and this time we will choose the first option. This will convert 4.5 to the fraction 9/2.